Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have our lecture 8 on debugging, profiling, and performance analysis. So this is more a conceptual topic, but in the end, there are lots of different practical tools which really are often used in HPC environments in order to get the best performance out of HPC applications. And we will look on some of them and also will have a kind of view through the idea of why performance is relevant. So we think about more speed up, why this is relevant. And on the other hand, we will also see certain traps that people do that do parallel computing and parallel programming. So before we go, however, in the materials of this lecture, let us review a little bit what we had the last time. And in review of lecture 7, I will quickly grasp on the idea of this generally understood idea of doing hybrid programming. And this is, let's say, more traditionally viewed, really the idea of using shared memory with OpenMP within one node, having the same access to the shared address space, if you remember, and then basically using MPI between the nodes, right? So this is distributed memory programming. So you combine shared memory programming with distributed memory programming here in order to scale up to many different nodes. And by having access, of course, with shared memory to the high-speed memory, you often can speed up some of the computations because, of course, we know that access to memory is ultra fast and you don't have to do message exchanges within the node. You can simply access the memory with OpenMP. And the communication is basically done through, reading and writing variables in the shared address space. However, we have also seen it has certain limits. The node at some point in time has not much more memory, and also the processing capabilities within one node is, of course, very limited. So in this sense, you go with the MPI then and basically have the opportunity to scale up, but doing the same modus operandi, so to speak, within the node using OpenMP. But as soon as you want to do, let's say, a more scale up of more different nodes, you really need MPI as well. And we have seen there are different ways how you can actually do this. And there are basically some of them which meaning that always the rank 0 has, let's say, the application space, usually the responsibility to do this step of using MPI to communicate to some other node. We know from earlier lectures, the reason why I want to do this is probably I want to share or obtain some data sets or data or some specific variables. So here we see an A as an example here that only when we have this kind of, we also learned in an OpenMP, basically program, I have different threads here, but this 0 thread master thread, so to speak, has always a very specific role. And also here it will take the lead or actually performing the MPI communication. This is rather clean. And with this, basically we as humans, we can follow suit with that relatively easy. However, we have seen there are other ways of how you can program it, where you basically have here always one thread at a time that does MPI, which is also another idea of controlling this a little bit, putting some constraint on so that you can actually understand the application of what it does. But it's not anymore limited to the, let's say, worker thread, as you see here. Here, every thread has the power to actually start an MPI communication if necessary, but it has to be only one in the parallel region. And then we have seen in C where we have a very relaxed manner of this, where basically every thread at all times is possible to do MPI calls. And with this, we have a quite complex scenario in order to understand the applications, and there must be very good reasons why that is done that way. And when we then look more deeper into this in the subsequent idea of lecture 7, we looked at there basically then these two modes, what you would say vector mode and task mode, where you basically would then keep, let's say, OpenMP and MPI in a way a little bit apart from each other. So it's clean code in a sense that you don't mix it up with the OpenMP regions and then also with the MPI. It has some drawbacks. Here you see overlapping of communication, computation here and there is a little bit limited because you wait properly until MPI send receives are maybe done, and then continue with another OpenMP parallel region, for example. However, for beginners especially, the vector mode is much more straightforward And only for experts, we would recommend then going to this task mode where you have an interleave really from MPI and OpenMP. And basically, this was something where we then had to look at some application scenarios. We know already from our earlier lectures the idea of the heat in the room equation that we had, where you basically have an average here formula computed where you need basically the values that are coming from your 4 neighbors as an example in a 2D scenario, and you average it and inform then basically your own heat in this particular tile. And we learned that this is, of course, the idea that we learned also before. When you have this time steps ideas, you see here 50 rounds, 200 rounds, so to speak, the time steps, we have to do this in the time step before in order to inform them for the next time step that you see here, T1, to basically compute the average correctly. And this was another application where you can do this in hybrid. It's a shared memory and basically another one, this Jacobi solver, which is then an MPI. And if you combine this, you can, of course, have the power then of the memory and the caches that you see a little bit here. The reuse of data in the shared caches is an important part here and there, which, of course, can you then, by properly implementing and programming this, use to your advantage if you do a hybrid programming, right? This is not something what you directly get out of distributed programming necessarily. However, we have also seen then in advanced applications that, you know, basically the idea of this halo regions that we had with this idea of the, you know, parallel flow model that we had, basically to have groundwater modeling understood, you crunch it up into this different 3D blocks, and each of these blocks would have some artificial halo regions in order to make this kind of message exchange possible. And then you would basically communicate between these blocks with MPI and the halo region exchange every time step before you start the next time step. And then essentially the computing can be done with shared memory within the node actually addressing these tiles. And this is, of course, just one example. We have seen the HPDB scan example now many times, where we basically clustering some data sets. And by doing so, we could use that basically in typical MPI, which you see here has a tail off at some point in time in terms of performance with increasing number of cores. The speed up was more and more limited. By using basically hybrid variant here with shared memory combined with distributed memory, we could scale much better, almost to basically optimal linear performance. And this is, of course, then one way of doing hybrid programming. And I have to say, as a disclaimer, these days also people talk about a different form of hybrid programming. And I introduced this just roughly because in lecture 9, we will come back to this when we talk about graphical processing units. You basically know from some of the early lectures that we always need the host CPU to have access to a GPU. And the way how it is usually programmed would be that because you just need the host CPU to basically get in the device memory, you know, basically data, you would not really compute on the CPU. So in the sense, it's, you know, idle and waiting, while the GPU does, you know, with lots of this different, let's say, many core processors, as we know, the computing. And at some point, you're back to the serial code of the CPU. By using this accelerator programming way, the CPU is wasted, but there's no other way because we usually, of course, have to go through the host CPU to go to the device memory and basically fill it up and work. But why not basically using perhaps in some points in the application also the host CPU while basically the accelerator is working as well? And this is an emerging form of hybrid computing, hybrid programming people nowadays talk about as well, meaning essentially using CPU processing power really, and also the GPU at the same time. But this will be also a topic we handle in lecture 9. So let us now rather move to lecture 8, which is about debugging, profiling, and performance analysis. And here also a short disclaimer. Of course, you could understand that we in Jülich, in the supercomputing centers worldwide, we really can fill a whole week just of doing this, what I have to present here in one lecture. That's why I also don't get a shock with the 77 pages. Today, it is just rather showing you some conceptual aspects later on about, you know, what could be wrong in programming in parallel. And that's why we have many, many pages. But in the end, it's important that you understand the general concepts. You don't have to know each of the particular programming problems you will run to. It is simply a lot of technology material that you have to understand. However, here I pick different pieces in order to understand what debugging and profiling now means if you move from a rather serial-oriented point of view to a parallel point of view, which requires tooling, right? And for tooling for debugging, tooling for profiling, and to understand and measure your application. Once you understand and measure your application correctly, you have the chance of doing performance optimization with certain tool sets we will talk about, like Scalasca, for instance, which is identifying certain, let's say, wrong parallel programmed aspects of your application. And with this, of course, you have the chance to really basically provide codes that have a very good performance, because you also can measure it, you can improve it, you have a yardstick you can actually measure against. So a very long lecture in a sense, but I keep it to our time slots, of course, just saying that many of these things, it's just good for you to see that. And you will notice that not everyone has of this, yellow blocks in the later part of this lecture. However, it's important to understand that tooling is required here. And with this code tuning aspects, you really know another complex aspect of parallel programming, because nobody has really these parallel programs directly perfectly programmed. It is quite usual to do this tuning. You come to tuning workshops, which are actually sometimes a whole week in Jülich, where you can basically perform code tuning based on this tooling. And this is really, HPC environment tools that support the programming that you learn here. And of course, across these lines in this particular lecture, you will notice it's quite hard and complex to handle this parallelism, which is another interesting part of it, why we need tooling. So let's start a little bit low level when you think about debugging. So this is something we share with computer science in general. So many of you know that a Java program, a C program, they all need to be debugged at some point in time, something we did wrong, some flaw somewhere that we actually have to first find and then to fix somewhere in a computer program. And we know here basically the idea of the name of this debug, or why it was a bug, is actually that here in this supercomputer once there was actually a moth found trapped in the computer, and that's how they came to the word of debugging, because they had to remove it and then it was working better. So this was really the first bug found, so to speak, and of course it sticks to us today. And when you think about examples, of course, you can imagine memory problems. You have basically wrong pointers. You have basically not defined variables correctly. We have buffer overflows or an array out of bound exception that many of you know. Then the code complexity is, of course, something where we always have some troubles here and there to perform debug away in the program or the application logic we didn't look at. And then, lots of different aspects. And it's a really broad topic in parallel programming. And you see here praise training. It's a training portal where we gather in the community of HPC lots of trainings. You will find also lots of large collections of these elements for debugging, for profiling, for performance analysis, really within this portal, because there are lots of training days, debugging days, tuning days that we basically do as workshops in these different centers. A couple of other terminologies you really need to know is a deadlock. So deadlock is a situation when basically one process waits for another to finish and vice versa. So something which is, so to speak, illustrated here a little bit an infinite loop, right? Because this process cannot proceed because it's basically waiting for another process to send me data first, and the other way around. So this process 3 also waits actually that the other process 1 is send me data first in order to send. So these would be waiting for each other forever and never finish. And this is kind of called a deadlock situation, which actually can come if you do concurrency in computation programming. Another one, which is also known here and there in the database world, is a bit lost update, but the race condition it would be that you have here different threads in the shared memory world, and you want to read basically those here out of memory for one thread, but you have also different threads writing X at the same time. So you would have no idea exactly when this is all happening more or less at the same time here, what value I will really actually receive. Is it 1 or 2? Because essentially they compete here already as a race condition, so to speak, around X. And then it really depends on who wins this race, who was first by an override, if I get a 1 or 2. And these are situations I don't want as a programmer, and could be critical basically on the application. So hence, when we think about the terminologies like debugging, where we really try to find an error first, while profiling is then more about aggregate statistics later, where we want to better understand our application and set a yardstick in order to then performance optimization, or then to perform really this performance optimization subsequently once I understood this application. So let's go first into debugging. And here we have, of course, many lessons learned that we know from typical software engineering and serial programming, which is, of course, by orders of magnitudes easier, but also has, of course, then lessons learned that we should take on, right? And this is the same for parallel programming, applications with MPI and OpenMP. You have the same engineering principles like check the error codes, integration testing, robustness. So whenever I did here in this course some examples, they are basically not the best example for it, I know, because here we want to rather show you the idea why parallel computing works and put an emphasis on it. When you have a real good parallel code, you want to make sure you have, quite a robustness of errors. You have meaningful variables and function names. You have really a good meaning of the variables, a very good readability of the code. They maybe even have descriptions, right, of functions, metadata, and so on. Of course, in a real environment, we also use, let's say, more or less today, SVN or Git, of course, and version control is, of course, also very helpful in these systems where we can rely on these days. And then really think about a more modular way, how to do application codes, how to do reusability of code elements. That is something which in previous codes or in older codes is not so obvious, because they're driven by physics and not by self-engineering principles. But today, I think more and more of these codes are moving towards this, basically integrating software engineering experiences with more modular aspects, plug-in elements, or basically then lots of elements to have reusability of code through libraries and so forth. However, many of those, as I said, don't really implement these approaches. And this is something, of course, where a community actively be working in with Matthias Boog, Helmut Neukirchen in interaction rooms. And so we try to improve and get more software engineering into these audiences, and have there also some publications and early examples, so to speak, in order to make better software. For instance, if you look at HPDB-Scan, it is a very good code done by a very good PhD student that actually had knowledge of software engineering principles at the same time, however, also, of course, for integrating the machine learning concepts and data mining concepts in order to do the algorithm. So the problem here relies, and basically the reasoning why people having trouble adopting this is, of course, the HPC complexity, right? Usually we do, let's say, code change, then compile and run trials. And this is, of course, kind of not really feasible in an HPC system. You know that. It's not an Eclipse in an integrated developer environment or so. Here you have always a scheduling script. You set it to this, scheduler. It will come back with a solution. So the whole loop of this compile run trial, so to speak, is much more longer, depending on where you end up in the schedule. Then basically here and there, you should also look at the absolute path. Is it the right program you actually even computed? Because if you have different versions and you improve them over time, you could basically mess up the job script and thinking, oh, that's the old executable and why I'm not improving. So you're debugging, you're modifying the code, you're compiling the code, but in fact, the job script has still the old executable, which was never newly compiled and still has the same error, while you believe that the bug is somewhere else. So lots of traps in this area where, basically things like which program name is something on Unix that you can use to really check it's the right program you just compiled. In generally, I would recommend, like all others, I think, basically in the HPC area, always do a stepwise approach. The same thing as I told you for the phishing simulation in your assignment. Basically start small, maybe small number of processes, keep the problem small. Once you solve that, the next step, then the next step. Fix the communication in that step, then the next step, and going more and more larger scale, one phishing population, one boat. Once you have done the catching with one boat and one phishing population, go to two phishing populations and one boat. And once that works, you go to 2 boats in the end, and then start with a storm, modeling, etc. So basically, this is an important part, because in parallel computing, these programs get quickly very, let's say, tough to read and to understand, because it's not anymore a very serial way of work. You know, the code is executed maybe on 20 cores at the same time, and you have to think about what that really means. So in general, you would say today we have really large-scale parallel codes that really have existing libraries, and it's getting better. But of course, also there, the versioning of this, the handling, the implementations of the physics within these libraries might actually vary also over time. So there's also a certain learning curve. And basically, bug prevention in that sense is always the best you can do, right? To check the HPC environments before you execute and run, let's say, a 24-hour job, you're going to make sure with just a quick rich program name that the ones that you want to really run is the same you actually specify in your job script. So then also when you think about our early course lectures and our early examples for MPI, I was always doing printf statements. And of course, this is no way to debug, but you will also see that this has very strong limits, right? It's of course a bit simple, but still also effective way. But once you come then to, let's say, 1024 cores doing something in parallel, you can imagine printf will be not really useful anymore, because they have simply too much outputs from all of these system processes really running. So also here, when you think about this, you know, constant cycle programming, it's error prone, and then you do another printf, compile, run, analyze output, and then you do again printf somewhere else to find another bug or so. Of course, this is really time consuming. Think about that printf, you know, means you change the code, you have to recompile the code, you put it in a batch script, it runs, etc. So here it is basically very tough to debug in the parallel world. And of course, you have this for one bug, and then you do the same exercise for another bug maybe. And with this, we see more and more the motivation of why we need tooling for this. It is really not appropriate in the end to do printf debugging when you have really high scale codes. Hence, we need there some technologies which are, let's say, so-called advanced debugging techniques. And of course, this is also something we share partly still with the serial computing community. So with people that do Java and you know, typical processes where you can debug. And one of the examples is here shown, basically, which is this DDD tool that you can use, a debugging open source GUI tool that you see here, where at least you can really do breakpoints. You can, you know, go through things you maybe know a little bit, of course, from things like Eclipse environment or integrated developer environments that have something like this always, let's say, more or less included. However, of course, applying these is basically not so easy. This, you know, let's say GDB and these tools that are around, because they're very similar, of course, to what we need, but still they are optimized for just one process usually, or basically for some environment on a laptop, on a normal kind of computing system. Of course, there's many advantages from crash inspection, function call stacks, the variable status. We have lots of insight there. And the setting of breakpoints is, of course, something which is very important. But it's still not so easy to apply those techniques, because in a sense, you have to attach them to different processes. I'll show you an example later. And the debugging tools that you have is basically known. I think GDB is broadly known. And there's also the kind of basic debugger that you get with DDD and so on, these kind of different GUI tools. And there are a couple of others around. Eclipse I already mentioned. They have a parallel tools platform for HPC, which can be used. And it's an integrated development environment that here and there helps. However, basically, when you come to tools like essentially commercial tools, they are really worth their money. You have to say the total view environment that you see here, and I brought you a video on it to understand it. You would say it's kind of the de facto standard if you really want to scale very high, to have this as a graphical debugging tool available for OpenMP and MPI applications, where you basically see here, you know, the different threads that are you working with in a parallel environment. You can see different frames. You can put breakpoints. You see here a little bit OMP parallel loops, where you basically see directly call stacks, source code, and this in a parallel fashion. So this is a very important one, and DDT is another one from Alinea. They are basically cost quite a lot, but they're also worth their money in this regard. And they have different features, of course, which I will also show you later a little bit. And then GPUs, we will come also in the next lecture a little bit through it, but of course they're very vendor-specific tools. For NVIDIA, for instance, GPUs, you will find some tool sets to also understand the application better than the usage of the accelerator device, memory, and so on. But yeah, we would say basically the debugging tools is a market which is really strongly dominated by commercial software, unfortunately, in a way. But as I said, they are also worth the money and should work correctly, because otherwise we waste lots of time. To understand a little bit serial and parallel relationships to these debugging tools is now basically the GDP. Some probably of you have already understood this in a previous, let's say, Unix course or so. So here you have a debugger, which is essentially for serial program tools. And how it works is you have a process running already. Basically very, very simple, could be any process you want, not necessarily an MPI application. But basically you have to attach this debugger then to an individual running process. And if you have an MPI process, it's the same way. You would have some, run with an MPI run, but we have this computing nodes. So you have to go to the computing node, not to the login node where this process is running. And then you attach the debugger to this process ID, which is running on this compute node. So you see it's already an added complexity what you have to do. And then you basically have to do different turns or externs to see, the output or the current, let's say, stack of the MPI process. And you have to do this for each individual process. And you see here how that works roughly. So on, you get the PID, but here you basically start the GDP with an executable, basically that we already have started with MPI run before maybe, and have basically then your PID thread aligned to it, where that is essentially the PID, which has, let's say, the typical MPI program maybe. And you can imagine now by doing this manually, every time you have an MPI process, is just infeasible. Think about this here. If you have, let's say, an application with 1024 cores, which is still a, let's say, low scale application, I would say these days, you don't want to do this 1,000 times, right? So here you see again why the tooling is really necessary. Which brings us then to Total View. It's a commercial debugging tool with a lot of capabilities. Also here we could do a 3-day training just on Total View, which is not the goal here of this lecture, just to sensitive, basically give you an indicator more that basically tooling is needed once you really scale up. And basically you can see that many of the centers, if not almost all centers in Europe, would have a commercial debugging tool probably that is available for the programmers there, or can be used in some, let's say, tuning and debugging, workshops. So here you can have also different code capabilities. It's probably clear because we know many codes in HPC are still Fortran, so you can also use it with this. But it is a, let's say, simple GUI, which has, the typical elements to go stepwise through applications. You see the stack trace. You also see basically the different variables and their content right now. You see the application logic, the functions where you just in, and where you basically can then, put breakpoints and understand the kind of execution. It has actually also a memory scape debugger, a memory tool debugger. That you see here a little bit, which is of course another important part, while here this part is maybe a little bit focused on the general parallelization terms of view, and then the communication paradigms, where you see here indirectly is somehow programmed a cycle that you can identify here now, basically, which is here and there good to see in the overall world of ranks, right? And you see this here, we just talk about 16 ranks here, but already you get the picture that a graph of, doing now maybe 1024 processes would be looking very complex. So here having tooling is of course a very great idea. And here we can identify problematic aspects of functional logic like the cycles or so very easily. And this distributed debugging tool is now the power, so you don't have to attach now your own rank to each of those debugger tools from total view. It is actually automatically getting access to all these elements. And then with the memory aspects, of course, I can really tune the memory to use as much as memory as I can. For instance, in hybrid programming, aspects where I said to you, it's really needs some tooling and also expertise to get a lot out of OpenMP / MPI programs that are hybrid, that these tools also enable you and help you then significantly of basically doing that. Brings us also now in a way to the next topic, which is related, which means profiling. Once a program is working perfectly in a way, you would say time it is for basically see how fast I am. So what is the timing of all of this? What is the basis runtime? And doing statistics of the execution time is something where profiling is in, and it helps you to understand that this is a usual idea how you do this. When you think you have an application, we just talked about this, basically the always kind of way of doing an optimized application. So you want to improve something, then you measure it with this profiling interfaces, and you perform the performance analysis, and then basically do some more tuning and optimized applications coming out of that. And it's a cycle that you can continue and continue. And you have tools basically like Scalasca and so on that also help you. And also some, let's say, metrics, which helps us to understand elements like strong and weak scaling you already know about, but also generic metrics of times of speed ups and so on. I will talk about you next. And it's really important that you think that this is a normal way to do it, right? So even if you think like in the beginning, you did an error with parallel computing or parallel algorithms and implementation, it's very common that you have this cycle. So don't worry, just go ahead with your application. Now, when we think about more why we do this, and when we think about the runtime, so how we can more conceptualize and basically put that in a kind of frame of reference that we know, you can always think about here with this kind of simple formula that we as parallel computing experts, we have a serial part of an application and a parallel part of an application, right? And this makes this one, which is, let's say, our application. So we'd have a serial part and a parallelizable part. And basically the serial part could be many things. You would argue, why can we not do everything in parallel? And here are some examples why we cannot do everything in parallel. Algorithmic limitations are there, maybe one after another, or basically we want to have the setup of the overall environment. The starting the parallel program takes some time. You have to distribute the executables on all the different compute nodes, startup, and basically this is a long thing. And then communication is here. Also one of the serializable part, I/O as well, with I/O devices and so forth. So, however, when we think about what we want to achieve is that in a way, we want to increase this by throwing more cores to this P part here, right? So basically, when you have here the time for a fixed size problem, this is a F, staying here for fixed size and basically going up. Then you have the parallel performance here, basically is like S plus P, the parallelizable part, divided by essentially this particular fellow, which is then the performance that you can use over time. And that is, of course, something where we say this is a serial performance when I have just, let's say, one time here. But we can exchange this by saying now with a parallel performance, we can add more N, right? Which N is the number of cores. For serial performance, I can't do that. I have this fixed, of course, and this would be perhaps the threads or so. But here we have the real cores and the real parallelization I can throw, so to speak, on this. And with this, you come to this interesting parallel performance here. If it's for a fixed size problem, of course, where S plus P is divided then by this, depending on N, right? And you can reformulate this P over N by saying 1 minus S, it's equal basically to P, right? It's a parallelizable part. It just takes the part of the other side of the equation and then divided by the number of N cores I throw on this problem in order to achieve a so-called speed up. Now, for this, in order to understand these times, we have to measure it. And one way of measuring is the so-called wall clock time or wall time, which you already know. It is important that this is essentially the elapsed time of the application. And as I said to you, with the wall time, you know already that the job was running against the wall. When I specify a beginning, a wall clock time that is 20 minutes, and suddenly the job is running for, let's say, 20 minutes as well, and then we're running against the wall. So essentially here we have the same thing. We want to measure basically the kind of the time. But the interesting thing is for us as application developers, we are not only interested in the CPU time, right? It's a bit misunderstanding here. So when we do this, the wall clock time is really the whole time, the actual time to complete a program, which is a sum of different terms. It's CPU time, IO time, and communication channel delay that we use in the MPI message passing, for example. So, and for this is basically the idea of to also have this as a way of, this is these few lines here, in large parts, they mean something like, we cannot use a computer always for free. We use something like core hours. And of course, for core hours and to know how much time you really have on the supercomputers, you need to measure the time as well from the scheduler. And over time, your core hours are deducted from your running time of the application until you have, let's say, not enough core hours left. And then you have to wait for the next grant period. So saying that this is indirectly a little bit related to so-called cost models. But for us in science, of course, the cost models are, let's say, just core hours that doesn't cost a thing. But if you go to, let's say, resource providers like Amazon or others in the cloud, you will see they have things like 24, bucks or US dollars for one, let's say, hour GPU time or other core hour times. Basically, this is a charging model where the time is, of course, serious. In other words, why we want to now then do performance optimization, we want to reduce that time. That means in one way, reduce cost. Let's say if you use a cloud, but also reduce cost in terms of core hours. So me as a scientist on these academic systems, I can use more from that time for more applications. That's why we have also the idea of making these high performance computing applications faster and faster. In other words, what we mean by this is reduce the processing time by increasing the number of processes, right? And this, of course, is something where we want to really kind of achieve. On the one hand, then really with this performance optimization aspect, so that my application is, using the systems as best as possible. So there's a certain degree where we anyway do, let's say, a reduction of processing time by just applying the number of processes that are more. However, I still use more core hours when I do more processes. That's obvious. But when I do so, of course, I want to do it in a performance optimized way. And with this, you really have the chance to, basically get the most out of the system. You see that a little bit here. One example here for the time to solution, we want to lower this. It's basically our key goal in HPC. And with the speed up, what you see here, you can basically see here a job which has a total number of nodes like 1 and 1 task. And when we include this to 2 nodes, you see we break down the time to 10 minutes. And then we can go on and do 4 nodes. And this is the usual way how you do it in high performance computing. For instance, you would do to the power of 2 increase of number of cores. So basically then we go double the core numbers or so usually, and come for later and later runs, you see we break down the time smaller and smaller until we're here with 3 minutes at something which 16 nodes, which we before had basically done in 20 minutes almost with just 1 node. So of course, huge speed up potential here to do so, but we will also learn that this has limits again, which we basically have seen in Amdahl's law, the serial limits that we have in a parallel application that we cannot augment. So you will find sometimes application, you cannot just make it better than 1 minute, even no matter how much things you throw at this, because let's say the performance is limited in the serial parts. So here's a simple MPI timing approach with Walltime. You see here, MPI gives you essentially there, let's say this kind of function that you can use to measure and you can maybe use also in your phishing application. And the profiling interface that you can then use for this, where also the performance analysis programs we will have in the second part of this lecture actually are basically built on, is this profiling interface from MPI, which essentially reroutes the typical MPI send, to this kind of profile interface MPI send version as an example here, in order to do, let's say, certain elements. You can, for instance, now increase a counter, because that's what we're also interested in. So basically you have used so many times this particular send operation as an example, or you take the time, right, when you entered the MPI send application. So here's an example of how that looks like from a profiling perspective, where essentially you have a wrapper function of this MPI call here, and you can do whatever you want here. Here I say basically just this counter, as I already alluding to before, and then I return this profiling send. Basically, it's a simplified demo code here, of course, but in the end, the cool thing is you have real program logic and you keep the MPI send as normal application run with the same, let's say, function here. That means you can basically turn off and on the profiling. And with this, you have still the same application. So it's nothing like we did before with printf statements now for profiling and do the Walltime again, and then removing printf again or so. Of course, you have to then basically, here link to the profiling library so that this will be basically executed in this specific way of linking it to this PMPI. But in the end, you have a very powerful mechanism of keeping your program, so to speak, the same way. And then there are other profiling tools available. You would say Valgrind is very good for profiling the memory usage of applications. VAMPIR is a tool which is a nice way of seeing a timeline of all your parallel, let's say, messages you do in MPI. We will have a look in Scalasca later, where basically you have the so-called trace-based profiling, and we will understand then what traces is later on. But essentially, you think everything you do in profiling, all the measurement will be actually locked to disk. And that's basically the idea of using these traces and then reanalyzing these traces and to do then performance analysis. As I also said, there are lots of tools in the commercial space available, and also those for GPGPUs. So here's Scalasca as one example, and we will hear a video about this basically later on from this particular tool set. And where you can see basically here the metrics we will also run through in the second part of this course as a motivation, and then where in the program you have it and where in the call tree. This is the application perspective, so to speak, how it is run on the HPC machine in a certain topology. So you essentially know really what is the problem in the performance you face, maybe late sender, where in the program it is, where basically here in this particular part of this application, and then basically which processes in the HPC machine running right now, basically what is there, how are they affected. And Valgrind is again an idea of really using essentially then, memory checks. It is also CacheGrind, kind of cache profiler where you can have really detailed simulations of a level 1 or 2 caches, which can be also, a great indicator for identifying cache misses subsequently or so. And as you know, cache is a very, very powerful tool. It's very fast, so it's good to use it to the best degree. However, this is really fine level tuning already, right? And basically it's an instrumentation framework where, again, you need probably a couple of days to really do this in a parallel environment. However, the memory consumption profiling and so on has, of course, very much offs if you basically are specifically doing OpenMP and shared memory programming and so on. And the way how that works is basically you again have here MPI exit statements, and you have the number of tasks, and you can basically put Valgrind there into the middle, which is then basically prepared to work with specific MPI libraries and so on, and also ready for, be used in a distributed fashion of sorts. Right, the other one that is basically existing is here this VAMPIR performance analysis tool that we basically gonna look in with all the different calls and trees. So let's look basically also then on this total view now in more detail within a video. So now, starting with debugging and Scalasca and VAMPIR and so on for performance analysis, we look in the second part of the course. So this is a total view debugger.
Hi, my name is Bill Burns. I'm the Director of Product Development and Product Manager for TotalView. And today I'd like to give you a quick introduction to TotalView, and I'll just do that through a demo of a debugging session. So I've started TotalView here, and we can see the interface on this. You're presented initially with a nice start page on here, which will direct you to how do you want to start your debugging session, if you're debugging an individual application or maybe a parallel program. TotalView is built from the ground up to debug complex applications that are utilizing multiple threads and multiple processes at a time. In this case here, I'm going to debug an application that will have multiple threads within it. So let's debug a program. I'm going to browse off and load my program here called Thread Workers. I don't need to set any other options at this point, so I'm just going to load the session. Here's my source for the application. And let me just start running the application on here. So this application is going to launch a GUI. So let me give a little room for that. And I'm going to hit go. So this is a Qt-based application that's going to simulate 4 threads doing work and then feeding a GUI thread with information on the results of their work. So if I hit start here, we see the threads working and providing information back up to the GUI thread. So let's halt the application with TotalView. And we can see in my process and thread view here an overview of my application and the 5 threads within it. Right now we're focused on thread 1.1 in the application. I can look over to the right to see where it stopped in the call stack on here. We're deep down in some system calls. I can refocus up to main to see that where we went through and into an exec routine on this. I can change my focus to any other thread by just double clicking on it, and I can see where those threads are. Again, they're in some system routines. I can go up to where there's code that they're executing as they're doing work. The power of TotalView really is focused around being able to manage complex applications with multiple threads and processes. So I can go through and go from high levels of either controlling groups of processes or threads, or I'll go all the way down to an individual thread. So let's run an individual thread here. So I'm going to change my focus level from group all the way down to thread, and I'm going to run this one GUI thread on here. So this highlights a feature with our process and thread view here, where we're showing an aggregated state of your job. So in this case, it's the threads that are going, and I have 4 threads that are still stopped and 1 that's running. Imagine an application with tens of thousands of either threads or processes. Having an aggregated display will allow me very quickly to see what's going on with my application. So let's focus on another thread here and run that thread. And what we'll see now is that that one thread is now feeding information up to the GUI thread, and as they're running, going through. Now, of course, with an application and a debugger, you want to be able to control it through breakpoints and so forth. So let's halt again, and we're focused on one of our threads, and let's just set a breakpoint in some code up here. So we'll go up through, just scroll up a little here, and I can set a breakpoint on a line, say 51 in here. Now by default, breakpoints are defined to a process width, which means when it hits, the entire process will stop. But I can change that to, say, a thread width. So let's go through and change that to thread, and then run my application again. So in this time, I'm going to change my focus to the whole process, and I'm going to run the process and go through. Now we can see that my one thread, thread 1, 2 in here, stopped at that breakpoint, and everything else is running, and we see everything updating in my application on here. So again, this aggregated state is very important to see the state of my job that's running out there. My action points view down below here shows me all my different breakpoints that I have set. TotalView has the ability to put evaluation points in, so you can run a bit of code at a particular stopping point in your program. You can also put watch points in that will watch memory, and if that memory changes, stop the execution of your program. And finally, we have barrier points for synchronizing processes and threads. On the right, we can look at local variables that are in the application and drill down into data structures and examine the data within those. I also have an advanced data view that I can look at data and structured data through that as well. TotalView has some advanced features along with it. We have a reverse debugging engine that records the execution of your program, and you can deterministically go back through that execution. Just like you're running forward and hitting breakpoints, you can do all the same in reverse. And it's a very, very powerful feature for finding bugs and also learning code. So this has been a really quick overview of some of the features in TotalView, some of the different aspects of the user interface on here. To learn more about all the capabilities of TotalView, please visit perforce.com and check out the TotalView page.
All right. So you have seen essentially that, before I could present anything of this so in detail, a short video on this makes surely sense to understand TotalView better. And the same is actually true later for Scalasca and these performance analysis tools, which will be next in order to do some performance optimization by really applying different tool sets and methods to a parallel application. So see you then.